a to the base b is equal to x. How do we write this in the exponential form? We can write it as b raised to x is equal to a. Both the equations tell us the same thing. Now before we move forward, there are a few fundamental properties we need to know. Let's discuss the first one. What will log of 1 to the base b be equal to? How do we find this answer? I encourage you to pause the video and find the answer to this. Say it equals x. In the exponential form, it can be written as b raised to x is equal to 1. Remember, the exponential form is what most of us are comfortable with. This can help us find the value of x. For the answer to be 1, the power here has to be 0. Do you remember that property of exponents? Any non-zero number raised to 0 is equal to 1. Hence, x here is 0. The log of 1 to any base will always equal 0. Log of 1 to the base 12 is equal to 0. Log of 1 to the base 250 is also equal to 0. That was the first fundamental property we looked at. Log of 1 to any base will always equal 0. Now let's move on to the second property. What will be the value of log of b to the base b? Give it a shot. Assume that it equals x. So in the exponential form, it can be written as b raised to x is equal to b. What will be the value of x here? Come on, it's easy. B to the power 1 will equal b. X will be equal to 1. The log of b to the base b will equal 1. If the argument and the base are the same, then the logarithm will be 1. For instance, the log of 4 to the base 4 will be equal to 1. That was the second property. The third one is pretty cool. It talks about the log of b raised to n to the base b. Assuming this equals x, try writing this in the exponential form. It is written as b raised to x is equal to b raised to n. It's pretty clear. X has to be equal to n. So the log of b raised to n to the base b will equal n. An example would be log of 11 cubed to the base 11 will equal 3. So these are the three fundamental properties of logarithms, and we don't really need to remember these as they can be easily derived. Along with the properties, there are a few conditions we need to know about. Let's see them on the right side of the board. The basic form of logarithm is written like this, where a is the argument and b is the base. Now for this to be valid, there are a few conditions about a and b that we need to know. Okay, first, the argument has to be greater than 0. This value here has to be greater than 0. So log of 0 to the base b is undefined, and the log of a negative number to the base b is also incorrect. But don't get confused here. The answer of the log can be 0 or negative. For example, as we saw here, the log of 1 to the base b will be 0. This is correct. And what will be log of 1/2 to the base 2? It will equal negative 1 as 2 raised to negative 1 is equal to 1 over 2 or 0.5. This is also correct. The answer can be 0 or negative, but the argument has to be greater than 0. What are the conditions for b? The base b has to be greater than 0 and it cannot be equal to 1. Yes, the base b cannot be equal to 1. So the log of a to the negative number base is incorrect. Why is 1 not allowed as the base? I want you to tax your brain a bit and come up with an answer. Why can't the base be equal to 1? Let's say the base was 1 and we have a logarithmic expression like log of a to the base 1 is equal to x. In the exponential form, it can be written as 1 raised to x is equal to a. What can be the value of x that gives us a? If a is 2, what will x be? If a is 5, what will x be equal to? we can't really come up with an answer because 1 raised to any number will result in a 1. Hence, this will be undefined. So these were the 3 simple primary properties of logs, and these were the conditions. With this, we can move ahead and solve interesting examples. Can we use logarithms to find the number of digits in a to the power b? Say the number is n. Let's represent the possible values of n using a scale. Now we make equal units with multiples of 10 so that we cover a range from 1 to 10,000. So if the number a to the power b is 9, it'll lie between 1 and 10. If it's 400, it'll lie between 100 and 1000. Now what if we find the log to the base 10 of these numbers? The log of 1 is 0. The log of 10 to the base 10 will be 1. What will be the log of 100 to the base 10? It'll be the log of 10 squared to the base 10. That will equal 2 times log of 10 to the base 10, which equals 2. And similarly, we have 3 and 4 here. Now the important question is, why did we do this? Let's see. Any number between 1 and 10 will have how many digits? Numbers like 3, 5.5, 9.8, they all have 1 digit to the left of the decimal point. And if we look at the log scale, we can say that if the number has 1 digit, then its log will be between 0 and 1. The logarithm will be of the form 0 point something. Okay, now look at the second part. Any number between 10 and 100 will have 2 digits, correct? Numbers like 22, 49.1 have 2 digits. And their logarithm lies between 1 and 2. It'll be of the form 1 point something. We will have 3 digits and 4 digits in these 2 parts respectively. And their logarithms will be between 2 and 3 and between 3 and 4 respectively. Now this gives us a very important result. 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, and 3 plus 1 is 4. When 1 is added to the number that we see in logs, we get the number of digits in the number. We can derive a very important property with this. If log of n to the base 10 is of the form x point something, then the number n will have x plus 1 digits to the left of the decimal point. This is how logarithms help us find the number of digits in a to the power b. Let's try out an example. There you go. We have to find the number of digits in this number, and we have been provided with these 2 logarithmic values. Needless to say, you aren't allowed to use the calculator. So let's try finding the log of the numbers. What will this be equal to? We can use the logarithmic addition identity to simplify this a bit. Log of a times b is equal to log of a plus log of b. Applying the identity, the right-hand side can be written like this. Can we simplify this further? Yes, we can use the multiplication by a constant identity. Log of a to the power n is equal to n times log a. Applying it to the first term, we get 12 times log 2 to the base 10. And applying it to the second one, we get 10 times log 7 to the base 10. And we have been provided with these 2 values. Substituting them here, we get this expression. Now these calculations are pretty easy. The first term can be written as 10 times 0.301 plus 2 times 0.301. 3.01 plus 0.602 will equal 3.612. And this will be 8.451. This sum equals 12.063. This is the log value of this number n. But is that what we are asked for? Not really. We are asked for the number of digits in the number n. And the rule we just looked at said that if the logarithm to the base 10 value is of the form x point something, then the number of digits in the number will be x plus 1. As the number x is 12 here, the number n will have 13 digits before the decimal point.